Welcome to The Explainer. Today, we're diving into the incredible piece of biological engineering you are using this very second, the human eye. It feels so instant, right? You open your eyes and boom, the world is just there. But the actual process of seeing, well, it's anything but simple. So, to really understand how we see, we're going to follow a single ray of light on its amazing journey, from the outside world right through the intricate machinery of your eye and all the way to your brain. Let's start that journey.
Okay, so how does the eye even start to capture an image? What are the basic mechanics that take raw light and begin turning it into something we actually recognize as sight?
You know, the easiest way to think about your eye is like a super advanced organic camera. Its main job is to bend, or as it's technically called, refract, light onto a sensitive screen at the very back. It's a beautifully simple idea, but as you're about to see, how it pulls it off is incredibly complex. So this path of light has 4 key stops. First, it zips through the cornea. That's the eye's outer window. Then the amount of light is controlled by the pupil, kind of like a camera's aperture. After that, it's focused by the lens before it finally lands on the retina, the sensor that actually captures the image. All these parts work together in this really sophisticated control system. Your cornea, it does the initial heavy lifting, performing most of the light bending. From there, the iris, that's the colored part of your eye, acts like a muscle, changing the size of your pupil to manage exactly how much light gets in. And all the while, these things called ciliary muscles are constantly working, subtly changing the lens's shape to fine-tune our focus. It's happening all the time without you even thinking about it. So after passing through the lens, the light finally forms an image on the retina. And here's a totally mind-bending fact. The image that forms on your retina is actually upside down. The retina's job is to act like a digital camera sensor, converting that upside-down light pattern into electrical signals. The optic nerve then zaps those signals to the brain, and it's your brain that performs the final magic trick of flipping the image right side up. But what happens when this super delicate system isn't perfectly calibrated? Well, for millions and millions of us, the image that hits the retina is blurry. This is where we get into all those common vision problems. So for a person with what we'd call normal vision, the closest you can bring an object and still see it clearly is about 25 centimeters, or, roughly 10 inches. This is what's known as the near point. Any closer and things start to get fuzzy. When vision problems pop up, it's often because this focusing power has changed. Now, the 2 most common focusing problems are myopia, which pretty much everyone calls nearsightedness, and hypermetropia, or farsightedness. If you're nearsighted, things up close are clear, but things far away are blurry. And for farsightedness, it's pretty much the exact opposite. So what's actually going wrong inside the eye? Well, it all comes down to where the light is focusing. In a nearsighted eye, the focus point for distant objects lands in front of the retina. It just doesn't quite make it. In a farsighted eye, the focus point for near objects would theoretically land behind the retina. So the light hits the sensor before it's had a chance to become sharp.
And the why of it all? It usually just comes down to basic anatomy. Nearsightedness often happens because the eyeball is just a little bit too long, or the focusing muscles can't relax enough to make the lens flatter for looking at things far away. Farsightedness is the opposite. The eyeball might be a bit too short, or the muscles can't squeeze the lens hard enough to focus on things right in front of you. But here's the good news. We've developed some absolutely brilliant and, honestly, pretty elegant solutions to fix these focusing errors and bring the world right back into sharp relief.
The most common fix, of course, is glasses or contacts. For myopia, or nearsightedness, you use a concave lens. That's one that's thinner in the middle. It spreads the light rays out just enough to push that focal point back onto the retina. For hypermetropia, you need the opposite, a convex lens, which is thicker in the middle. It helps bend the light more, pulling the focal point forward so it lands perfectly on the retina. Simple, but it works.
Now, for a more permanent solution, there's LASIK surgery. And it is a remarkably precise procedure. A surgeon creates this incredibly thin flap on the cornea, folds it back, and then uses a cool ultraviolet laser to literally reshape the corneal tissue underneath. To fix myopia, they flatten the cornea a little bit. For hypermetropia, they make it a bit steeper. Then the flap is just laid back down to heal. You're essentially getting a corrective lens carved out of your own eye tissue. It's amazing. But focusing problems aren't the only challenges our eyes can face. There are other conditions out there that affect totally different parts of this complex little organ.
One of the most common is cataracts. This is what happens when the proteins that make up your eye's natural lens start to clump together, turning that once clear lens cloudy. It's kind of like trying to look through a foggy window. This is often just part of aging or can be caused by long-term exposure to UV sunlight.
Now, cataract surgery involves taking out that cloudy natural lens and replacing it with an artificial one. For decades, this was just way too expensive for many people around the world. But that all changed in 1995, thanks to a Nepali doctor named Sandrik Ruit. He developed this revolutionary, low-cost lens that made sight-restoring surgery affordable for millions of people. A true game changer. Okay, let's go back to the retina for a second, because it has its own cool complexities. It uses two different types of light-sensitive cells, rods and cones. Rods are incredibly sensitive, and they give us our black and white vision in dim light. Cones, on the other hand, need bright light, but they are what let us see the world in vibrant color. So when there's a problem with those cone cells, it can lead to color blindness. We have 3 types of cones, for red, green, and blue light. And most forms of color blindness happen when the red or green cones are faulty, making it tough to tell the difference between those shades. And here's a cool little aha moment. This also explains why we can't really see color in the dark. It's because our cones just aren't activated. And if the problem isn't with the cones, but with the rods, well, that can lead to night blindness. The pigment in those rod cells actually needs vitamin A to work properly. So a really severe vitamin A deficiency can mess with your ability to see in low light conditions because the very cells responsible for it just aren't working right.
When you just step back and think about it, from bending light to detecting every color of the rainbow, from focusing on a book to gazing up at the stars, our eyes perform an absolutely astonishing number of tasks every single second. They really are a testament to nature's power as an engineer, both incredibly resilient and remarkably fragile at the same time. I mean, we've gone from simple glass lenses to surgeries that literally reshape the eye itself, and the technology is only getting better and better. It really raises a fascinating question. As we get better at not just correcting, but enhancing our vision, what new frontiers are we going to see? What lies beyond the current limits of human sight? Thanks for joining us on The Explainer.